Okay, my name is Austin, and this is my video for Physics 2211 Lab 2, which is about the motion of a falling object. So the purpose of this lab was to observe the effect of gravitational force and drag force on the position and velocity of a falling object. The main physical principles used in this lab are Newton's first law, which says an object will maintain a state of motion unless acted upon by an outside force. They say the object is starting from rest and isn't going to move up or down without the forces of drag and the force of gravity acting on it. And we're also using Newton's second law, which is the equation force equals mass times acceleration, and also a couple other formulas, including the position update and velocity update formulas, which are derived from it. The models we're using use the second law equation along with the drag force equation, which is simplified for this experiment, but for our purposes, it's just the force is b times v squared, where b is a drag constant, which is unique to each object, kind of based on its shape and some other stuff, and v is the object's velocity. The results of the lab show that the gravitational force is stronger than the drag force and will pull the object downward, though the drag force does slow it down. The system in this experiment was a paper ball whose mass was 0.0227 kilograms. The surroundings are literally everything else in the universe, including the room that the experiment took place in, and the air surrounding the ball. Here's the initial position of the ball according to the coordinate system we used in Trekker, and the object was dropped from rest, so the initial velocity is 0. Basically, how the experiment went was the object was dropped from a height, and I used Trekker to track its position at intervals, and then used the information to determine the object's velocity, and used the data in the computational models. So there were two models that I used for this lab. The first one only uses the force of gravity and assumes there are no other forces acting on the object other than gravity to counteract it, so it's free to accelerate infinitely. For this one, I'm going to ignore this part and these two lines right here, and just focus on this line and this part. Now, the model uses this Newton's second law equation, force equals mass times acceleration, to calculate the force right here, and then the velocity and position update formulas to find those values at each interval. Here's the mass of the ball times g, which is 9.8, or the acceleration due to gravity, and then times j hat, which just gives the force of direction. The second model includes the drag force, which counteracts gravity. Here you can see that it calculates the drag force, which is b, the value of which I found by using some trial and error to make the model look close to my actual data. So it's b times the magnitude of the ball's velocity squared times j hat again, which just gives it a direction. And then it calculates the net force by adding the forces of gravity and drag. And then again, it uses the net force in the position and velocity update formulas to find the values at each interval. Here I plotted my data for the model not including drag, the model including drag, and my actual observation data all on one graph. You can see that the model without drag shows the object continuing to accelerate infinitely since there's no force counteracting gravity. You can see that the slope continues to get steeper going down. The model with the drag includes a force counteracting gravity, so you can see that it's accelerating less steeply than the first model. This one and the actual observation data are pretty consistent, so I would say that the second model can reasonably be relied on for these kinds of experiments. Some potential sources of error here was that the object wasn't perfectly spherical, since it was just a paper ball, or it wasn't dropped from high enough to get a good observation. To answer the question about which model predicts a terminal velocity, you can see that in the model including the drag, the velocity gradually approaches a single value, which seems to be right around or a little less than 3, as the drag force's magnitude becomes equal to the force of gravity's magnitude, eventually resulting in a constant velocity. In the case that the object is thrown downward instead of starting from rest so that it has an initial velocity, the final terminal velocity would be the same, but if it was thrown down, it would reach a terminal velocity in a shorter amount of time compared to starting from rest. Because you can see right here, starting from rest, it reaches terminal velocity for about 1 to 1.3 seconds. But starting with a negative velocity, it reaches it from about 0.8 to 1 second. But yeah, that's pretty much it. So thank you for watching.